The next topic that we have is electrochemistry. This is also referred to as a redox reaction because a lot of the reactions that we have are a combination of reduction reactions and oxidation reactions. Oxidation is loss of electrons and reduction is gain of electrons. We can use the acronym OIL-RIG to reference oxidation and reduction. Oxidation number. These are charges, actual or hypothetical, assigned based on a set of rules. The numbers are assigned to atoms after losing or gaining electrons in a chemical reaction. For example, you can change Fe2 plus to Fe3 plus, and in the process, the oxidation number of Fe2 plus, which is plus 2, changes to plus 3, which means there is an increase in oxidation number. The process is also referred to as oxidation. In the second example, oxygen can gain 2 electrons to change into the oxide ion. Oxidation number of oxygen, the unreacted element, is 0. Whereas in the oxide ion, the oxidation number is minus 2. There is a decrease in oxidation number. Therefore, the process is referred to as reduction reaction. Oxidation leads to an increase in oxidation number, and reduction leads to a decrease in oxidation number. So this can be a generalization which can be used while trying to identify oxidation reactions and reduction reactions. Here is a graphical representation. Oxidation number increases when there is oxidation, and oxidation numbers decreases when there is reduction. That is the premise on which we will be proceeding. Here are some examples of oxidation. Magnesium changes to Mg2 plus by losing 2 electrons. The oxidation number increases from 0 to plus 2. Sodium loses an electron and changes to Na positive. Oxidation number increases from 0 to 1. Aluminum changes from Al to Al3 plus. The oxidation number increases from 0 to plus 3. Sulfide ions has an oxidation number of minus 2, and the minus 2 value changes to 0. There is an increase in oxidation number. Fe2 plus changes to Fe3 plus. There is an increase in oxidation number from 2 plus to 3 plus. Fe changes to Fe3 plus. Again, there is an increase in oxidation number. Therefore, the process is oxidation. And finally, Sn2 plus changes to Sn4 plus. And this again represents an increase in oxidation number from 2 to 4. Therefore, all of these examples are examples of oxidation. And in all of these cases, we see an increase in oxidation number. Here are some examples of reduction. Cl plus electron gives you Cl minus 1. Or the chlorine atom gets reduced by gaining electrons. When a reaction gains electron, there will be a decrease in oxidation number because we are adding negative charges. So 0 changes to minus 1, decrease in oxidation number. So this is a change that we are looking at, and therefore the reaction is a reduction reaction. Oxygen gains 2 electrons and changes into oxide ion. There is a decrease in oxidation number from 0 to minus 2. Nitrogen gains 3 electrons and forms the nitride ion, and the decrease is 0 to minus 3. Fe3 plus gains 1 electron and changes into Fe2 plus. The oxidation number changes from plus 3 to plus 2. Fe3 plus can gain 3 electrons and change into Fe with 0 oxidation state. Therefore, there is a decrease in oxidation number. Again, the process is reduction. Again, we are restating the definition of oxidation number. These are charges, actual or hypothetical, assigned based on a set of rules. These rules depend upon the group number to which the element belongs, or the valencies, and also the differences in the electronegativity. Here are some rules for assigning oxidation number. The oxidation number of an atom in the elemental state is always 0 because it has the same number of protons and electrons. So if you look at this periodic table, any element that you take, since they have the same number of protons and electrons, they will have a 0 oxidation state. So in an uncombined state, all elements, they have 0 oxidation state. The oxidation number of an element or a monoatomic ion is the same as a charge on the ion. So if we're looking at ions, for example, if you look at Fe2+, the 2+ represents the oxidation state of that ion. Sulfur with the 2 negative charge, which is also referred to as a sulfide ion, has an oxidation number of -2. Chromium 3 positive or trivalent chromium, the oxidation number is +3. Nitrogen with 3 negative, which is a nitride ion, has an oxidation number of -3. This is what we mean by saying a monoatomic ion has an oxidation number which is equals to its charge. In a binary compound of a metal and a non-metal, the metal always has a positive oxidation number and the non-metal has a negative oxidation number. For example, in sodium chloride, sodium is a metal and chlorine is a non-metal. Since metals are electropositive, they tend to lose electrons and become positively charged. Non-metals are electronegative, they tend to gain electrons and form negative ions. So in this case, sodium will be +1 and its oxidation number is 1. Since it belongs to group 1, has a tendency to lose 1 electron. Chlorine belongs to group 17, tends to gain electron and form a chloride ion. Therefore, the oxidation number is -1. Calcium sulfate dissociates to give you Ca2 positive plus SO4 2 negative. Again, this is a binary compound involving a metal and a polyatomic ion. The sulfate ion is a polyatomic ion. Calcium is the metal, therefore the metals will be positively charged. The valency of calcium in group 2 is +2. Therefore, the oxidation number is +2 for calcium. And the oxidation number for the polyatomic ion is its charge. So -2 is the oxidation number for the polyatomic ion. The sum of the oxidation numbers of the constituting atoms in a polyatomic ion is what we are referring to as the oxidation number of the polyatomic ion. In compounds formed between nonmetals, the element with higher electronegativity is given a negative oxidation number. We are looking at polar covalent bonds or molecules with polar covalent bonds. For example, if you're going to look at the formation of hydrogen chloride or HCl, we know that HCl, the chlorine is more electronegative. The value of electronegativity of chlorine, if you look, you will find it to be 2.9, and the electronegativity of hydrogen is 2.1, which means chlorine is more electronegative and tends to be delta negative charged, and the other will be delta positive charge because of the polarity of the bonds. When we are considering oxidation numbers, we consider there's a total transfer of electrons, even though that doesn't happen. It's a hypothetical concept. So chlorine tends to gain the number of electrons as determined by its combining capacity. So in this case, it will be -1. So hydrogen will have an oxidation number of +1 and chlorine will have an oxidation number of -1. Now let's try what the oxidation numbers of hydrogen and oxygen will be in water. Hydrogen has an electronegativity of 2.1 and oxygen has an electronegativity of 3.5, which means oxygen is more electronegative and will be negatively charged. Since the valency of oxygen is -2, we will see that oxygen has an oxidation number of -2 and hydrogen has an oxidation number of +1. So we can use electronegativity difference to assign positive and negative values for the oxidation numbers, and these values will be full hole charges because it's a hypothetical concept that we are using to assign values which can be used to balance equations and also predict redox reactions. In all compounds of hydrogen, the oxidation number of hydrogen is given a value of +1. That's the most common oxidation state of hydrogen. There are certain exceptions, and the exceptions are metal hydrides. Sodium hydride and lithium hydride are examples where hydrogen is the more electronegative element and the metals are the ones that are more electropositive. Therefore, hydrogen gains an electron and forms the hydride ion when you have 2 electrons in the first shell. So, in exceptional circumstances like metal hydrides, hydrogen will have an oxidation number of -1. The regular oxidation number for hydrogen is +1. The exceptional oxidation number is in metal hydrides and the value is -1. In compounds containing oxygen, it is always assigned a value of -2. That's the most common oxidation state. But there are exceptions here. Peroxides or hydrogen peroxide or sodium peroxide, where oxygen tends to have an oxidation number of -1. Again, if oxygen tends to combine with fluorine, it forms fluorides, 2 of them. And we already know that fluorine is the most electronegative element in the periodic table. So if you look at the compound and the formula written, it's written as OF2. Usually the first element is more electropositive and the second one is electronegative. Because fluorine is the more electronegative element, it tends to gain the negative charge or negative oxidation number, which is -1. 2 of them are there. Therefore, that makes the oxidation number of oxygen +2 in OF2. So this is an exception. The second compound fluorine can form with oxygen is O2F2. And in this case, when you calculate the value of the oxidation number of oxygen for a single atom, it is found to be +1. Regular oxidation number of oxygen in most of the compounds is -2. Exception is peroxides is -1. Fluorides, 2 of them. In O2F2 it's +1. In OF2 it's +2. You may want to recall this information. It may come in handy while balancing equations. For neutral molecules, the sum of the oxidation numbers is always 0. What I mean by a neutral molecule is a molecule like carbon dioxide, water, ammonia, all of these are neutral molecules. So let's take the example of carbon dioxide. CO2, the total charge of carbon plus oxygen is 0. We don't write carbon dioxide with a charge because the value is 0. So if you know the oxidation number of oxygen, you can calculate the oxidation number of carbon. So the total oxidation number for the molecule is oxidation number of carbon plus oxidation number of oxygen, which is given as 0 because it is a neutral molecule. So if X is the value for the oxidation number of carbon, we can add it with the oxidation number of oxygen. There are 2 oxygens in carbon dioxide, that is this 2, multiplied by the oxidation number, which is -2. So we can say X minus 4 is equals to 0, and the oxidation number or the value of X is going to be +4. So the oxidation of carbon is +4 in carbon dioxide. Let's solve and determine the oxidation number of sulfur in sulfur trioxide. X is the oxidation number of sulfur plus there are 3 oxygen atoms. So we have this 3. The oxidation number of oxygen is -2. So X minus 6 is equals to 0. Therefore, X is equals to +6. That's the oxidation number of sulfur in sulfur trioxide. For complex ions, the sum of the oxidation number is the charge of the ion. So we are going to look at two different situations here. We refer to something as a complex ion. The second example is more precisely a complex ion. The first example is the dichromate ion, Cr2O7 negative. The oxidation number of this polyatomic ion, like I said in the earlier case of sulfate, -2 is the oxidation number of Cr2O7 2-, which means the sum of the oxidation numbers of chromium plus oxygen is equals to -2. So this information can be used to determine the oxidation number of chromium if that is unknown to us. There are 2 chromiums in dichromate and there are 7 oxygens, and the net charge is equals to -2. So if you consider that the oxidation number of chromium is unknown, we can say it's X or we have 2X. The oxidation number of oxygen is -2 in most of the compounds. And there are 7 oxygen atoms, so 7 times -2 plus 2x is equals to -2, or 2x is equals to 12. We're just multiplying these two numbers and subtracting the 2 from it, or we can say x is equals to 6, which is hexavalent chromium. So each chromium has an oxidation number of +6. In the second example, the complex compound that we have here is COCl4. This is truly a coordination compound, hence a complex molecule. The IUPAC name for this compound is tetrachlorocobaltate-2 ion. Normally, when you're asked to determine the oxidation number, we don't give you the name, because the name also includes the oxidation state of cobalt. We are going to calculate the oxidation number in this case. We have 1 cobalt, we have 4 chlorines, so 1 times X plus 4 times -1. So this 1 represents how many cobalt is there, X represents the oxidation state of cobalt, 4 represents the number of chlorine atoms, and -1 represents the oxidation number of chlorine. So we can say X minus 4 is equals to -2. Or X is equals to +2. Oxidation number of cobalt is +2. So we can determine the oxidation numbers of metal ions in complex compounds using the algebraic addition based on the common valencies of the elements that are forming the complex ion. So here are certain reactions that are given to you, and you have to determine whether these reactions are redox reactions or not. I'm going to work 2 examples for you. The rest of the examples you can work out by yourself. We have already seen that an increase in oxidation number indicates oxidation and a decrease in oxidation number indicates reduction. So we want to check out to see whether the reactions are redox reactions. Always redox reactions are complementary. There will be an oxidation reaction and there will be a reduction reaction. So we're going to look for situations where we find that there is change in oxidation number for one element by increasing and a decrease for the second element. For the reaction between hydrogen sulfide and sodium oxide producing sodium sulfide and water, we're going to write the oxidation numbers based on the number of elements that we have. We have 2 hydrogens in hydrogen sulfide, 1 sulfur atom or the sulfide ion. We have 2 sodium atoms and 1 oxide ion on the reactant side. On the product side, you have 2 sodiums and a sulfide ion, 1 sulfur, and water with 2 hydrogens and 1 oxygen. I just split them up now in the second line. 2 hydrogens, 1 sulfur, 2 sodiums, and 1 oxygen on the reactant side. Again, 2 sodiums, 1 sulfur, 2 hydrogens, and an oxygen on the product side. We can assign the oxidation number. So here for hydrogen, 2 times +1 is the oxidation number of 2 hydrogens. The oxidation number of sulfur is -2 in hydrogen sulfide. Similarly for sodium, it is 2 times, this X is 2 times +1 because sodium has an oxidation number of +1. Oxygen again has an oxidation number of -2. So let's see how it looks like. these are the total oxidation numbers based on the number of elements that you have. The total oxidation numbers for 2 hydrogen is +2. On the product side, again, you have 2 hydrogens, and that is also +2. Therefore, there is no change in oxidation number for hydrogen. Sulfur. The oxidation number of sulfur on the left is -2. The oxidation number of sulfur on the product side is -2. No change in oxidation number. Sodium on the left has +2 oxidation number. Sodium on the right has +2 as oxidation number. Oxygen on the left has -2 as the oxidation number. Oxygen on the product side has -2 as the oxidation number. Therefore, we find that the elements on the left and right, there is no change in oxidation number. Therefore, this reaction is not a redox reaction. In the second example, we are looking at the reaction between calcium and water to form calcium oxide and hydrogen gas. On the reactant side, you have 1 calcium in the elemental state. In water, there is 2 hydrogens and 1 oxygen. Those are the reactants. And on the product side, you have calcium in calcium oxide and 1 oxygen in calcium oxide and 2 hydrogens in hydrogen molecule. We are going to write the oxidation numbers. For an element, the oxidation number is always 0. So calcium has an oxidation number of 0. Hydrogen, the oxidation number is +1 in most of the compounds. Oxygen, the oxidation number is -2. We had already seen that. Again, in the product side, calcium exists as Ca2 positive. Therefore, this would be Ca2 positive, making the oxidation number of calcium +2. Similarly, the oxidation number of hydrogen is 0 because it's in the elemental form. So we're going to compare the oxidation numbers. So here, calcium on the reactant to product is changing from 0 to +2. Hydrogen is changing from +1 to 0. Therefore, there is a change in oxidation number for calcium and hydrogen. And therefore, let's see what happens. The oxidation number of calcium, 0. Calcium +2, increase in oxidation number. Therefore, calcium is undergoing oxidation. Hydrogen, for 2 hydrogens, it's +2. For H2 molecule, it's 0. Therefore, there's a decrease in oxidation number. So calcium is being oxidized and hydrogen is being reduced. Therefore, this reaction is a redox reaction. Now, you can solve the remaining examples and you can predict whether those reactions are redox reactions or not. Here are the answers to it. First reaction is not a redox reaction. Second one is a redox reaction. We had already seen and explained it. Third one is a redox. The fourth one is not a redox. The fifth one is not a redox. Sixth one is also not a redox reaction. Here are some examples for you to determine the oxidation numbers. The elements that are underlined are the ones that you have to determine the oxidation numbers for. MnO4 2-. So I'm going to solve this for you. So the total charge is the oxidation number of the polyatomic ion. And I need to determine the oxidation number of manganese. Oxygen is not a peroxide, it's not a fluoride. Therefore, the common oxidation number can be applied. So I'm going to say 1 manganese times X plus 4 oxygens times -2 is equals to -1, which means X minus 8 is equals to -1. X is equals to 7. So the oxidation number of manganese is +7. It's a good idea to review your formulas of polyatomic ions with charges, because that will come in handy while balancing equations and writing redox reactions. It's an expectation that you know the formulas of all the polyatomic ions that you have learned so far. These are the answers. Check to see if you can solve them to obtain these values. There will be multiple choice questions where you have to determine the oxidation numbers. Those are the very basic, simple questions that you can get from this section. You will be expected to apply the rules for oxidation numbers. So I will not ask you what the rules are, but you will be expected to apply them while balancing equations, calculating oxidation numbers, or predicting redox reactions. That's it for now.